And then if you would like to, let me hold on, let's do this real quick. Go to participants, mute all. And then Anne-Sofie, if you would like to unmute yourself, I will do the introduction and we can go from there. All right. It is my pleasure to announce Dr. Anne-Sofie Ahm, an assistant professor at the University of Victoria in British Columbia, Canada. Dr. Ahm completed her PhD at the University of Copenhagen and a postdoctoral fellowship at Princeton University. Her research group at UVic takes a multidisciplinary approach combining isotope geochemistry, paleoclimate studies, Earth system modeling, and geobiology. Broadly, Dr. Ames' work uses chemistry of sedimentary rocks to reconstruct past Earth environments, with a particular focus on the coevolution of climate and life during the Precambrian. Thank you for being here with us today. The floor is yours.
All right, thank you so much. Can you hear me? Okay. Um, so, first of all, thank you for the opportunity to share some of the work I've been doing through the last couple of years. And I'm going to be talking about calcium isotope constraints on Mesoarchean seawater chemistry. So, what I really want to get into in this talk is thinking about what was the bulk carbonate sink in the Precambrian, and particularly in the Mesoarchean. So carbonate minerals have formed on Earth's surface for more than 3.5 billion years. And this precipitation of calcium carbonate in the ocean is an important sink for alkalinity, and it therefore modulates the concentration of CO2 over much of Earth history. However, we really don't know much about what this important alkalinity sink looks like through large parts of Earth history. So for example, here I'm showing a figure taken from Peterson and Husson, 2017, that shows the proportion of sediment preserved in the geological record. And so one thing you'll see here is that we have this deep sea sedimentary archive that goes back into the Mesozoic. And then what we really only have in deep time is the shallow marine sedimentary archive. So the reason that we lose this deep sea record is because ocean crust is continuously subducted. So we just don't have preserved this archive as we go back in time. Um, Also, although we do have the shallow marine archive preserved, we don't have the preservation of all our sediments. So as we go back in time, we really lose this window into what the bulk carbonate sink looks like. And one thing you might notice looking at this figure, it doesn't even go back into the Archean. So we really just have a fraction of our sediments preserved. And so it begs this question if there might have been a hidden, potentially deep water pelagic carbonate sink in the Precambrian and in the Archean, and that this sink is just simply not preserved in the geological record. So the tool I want to use to get at these questions is I want to use calcium isotopes. So I'm going to give you an introduction to the global calcium cycle. So calcium is a major element in calcium carbonate minerals. And calcium carbonate formation is the primary pathway by which carbon and calcium is returned from the ocean atmosphere system and into the solid Earth. So we can break up the calcium cycle into its sources and sinks. So the main sources are continental weathering and hydrothermal inputs. And the dominant sink is the deposition and burial of carbonate minerals. So over long time scales, we're going to assume that the calcium cycle is in a steady state. So we're going to set the sources equals to the sinks. So when we look at the calcium isotope mass balance, we're thinking about the ratio of calcium 44 to 40 in carbonate sediments. And the standard, I'm going to normalize these values to our modern seawater. So in other words, when I say 0 per mil, I mean the delta 44 value of seawater today. So on long time scales, I'm going to assume that the input of calcium isotope values into the ocean, globally integrated, is similar to bulk silicate Earth. So bulk silicate Earth has a calcium isotope value that's around 1 per mil depleted relative to modern seawater, more precisely minus 0.96 per mil. And the main calcium sink is our carbonate minerals, and carbonate minerals are fractionated relative to the seawater where they form. In other words, calcium 40 preferentially goes into the carbonate mineral lattice. So that means that seawater is heavy relative to our carbonates. So we can also write up a simple calcium isotope mass balance. In a steady state, we know that what goes in must comes out. So in other words, the delta 44 calcium value of our inputs must equal the outputs. So assuming that our inputs equal to bulk silicate earth and that our outputs are broken down into the calcium isotope value of seawater minus the fractionation factor of our bulk carbonate sink. So we can use this very simple isotope mass balance equation to think about what controls the calcium isotope value of seawater through time. So here I've simply just rearranged this equation. And what you can see, this is just a simple linear equation, y equals mx plus b. And so that's what I'm plotting here in this figure to the right. So on the y-axis, we have the delta 44 calcium value of seawater. And on the x-axis, we have the fractionation factor of the bulk carbonate sink. For example, in the modern seawater is 0 per mil. And so you see that our bulk carbonate sink must have a value close to -1, which matches the input value from bulk silicate earth. So from this equation, we can also see that the long-term calcium isotope value of seawater is controlled by two factors, the isotope value of the input, right? And the isotope value or the fractionation of the bulk carbonate sink. So in other words, if we can reconstruct the calcium isotope value of seawater through time, then we can gain insight into what is the fractionation factor of this bulk carbonate sink. So I want to show you an example before we dive into the Precambrian, the Mesoarchean record. And so this is the calcium isotope record going back through the last 160 million years. So has the calcium isotope value of seawater changed through time? I think we have compelling evidence that it has. So this is a figure from a study by Goffman and colleagues from 2016. And these authors compiled a bunch of different archives, specifically looking at fossil corals here in red. And while you see that there are some scatter and disagreement between these archives, there is a general trend as you go back in time from the Cenozoic and into the Mesozoic, our inferred calcium isotope values of seawater decrease. And this decrease is in the order of around half a per mil. So this increase as we go towards the modern, or decrease as we go into the Mesozoic, that has been inferred from multiple archives. And what this implies is that the isotope value of our bulk carbonate sink must have been heavier in the Mesozoic. Or in other words, as we go towards the modern, we must be removing more light calcium in order to drive seawater heavy. So going back to the simple linear model I showed you before, we can now also plot on a line. If seawater is minus 0.5 per mil in the Mesozoic, that would imply that the fractionation factor of our bulk carbonate sink is around half a per mil. So this change in the fractionation factor has been linked to the evolution of the pelagic carbonate sink in the Mesozoic. And so that's why we are driving seawater heavier as we go into the Cenozoic and towards the modern. So one thing that I'm really interested in is thinking about extending this record back in time, as far back as we can go, all the way into the Archean. So one of my students has kindly helped me put together this record, gone through all the literature and compiled a bunch of calcium isotope studies. And I will just note that I don't think this is entirely complete, but I do think this shows a representative picture of what calcium isotope values in carbonates look like through time. So there are a few things here to notice. First of all, we see this increase that I just showed you, where we go from values around minus 0.5 to 0 per mil in the Cenozoic. And as we go further back in time, there are no sort of obvious trends. There seems to be this long-term stasis. Interestingly, the average value through each of these bins is very close to bulk silicate Earth, but there's a lot of scatter. So if we really want to try and figure out what this record shows, and more importantly, if we want to try and reconstruct what is the calcium isotope value of seawater through time, we have to understand what the scatter means. So to get at that, I want to show you this compilation here of calcium isotope values in modern and recent carbonates. And there's a lot of different archives here, but what I really want you to look at is just the x-axis. And notice that the range that we see is around 2 per mil. So this essentially encompasses all the scatter that we see in the geological record. So there are a lot of things, a lot of factors, processes that are important to think about if we want to try and understand what is the fractionation factor of calcium isotopes into different carbonate minerals. And so I highlighted 4 different processes that we need to think about. The first one here is biomineralization of vital effects. So different types of organisms fractionate calcium isotopes differently into their skeletal material. If you just look at here a compilation of different modern skeletal calcite, we have a range here of more than 1 per mil. We also have a range if we just look at different pelagic organisms, skeletal aragonite, etc. This is an older figure from 2012, but showing the same thing, looking at a bunch of different types of organisms and a calcium isotope value relative to seawater. And we see again, a very large range in what the delta 44 value is. Luckily for us who are interested in the Precambrian, we can mostly ignore these biomineralization effects because we don't really look at skeletal carbonates most of the time. But another thing we do have to think about is carbonate mineralogy. So different carbonate minerals fractionate calcium isotopes differently. Here I'm just highlighting in this compilation some of these different minerals. So we have aragonite that's isotopically depleted with an average value maybe around -1.5, -1.4. I should say here the color here is the strontium to calcium ratio. So we see here that aragonite has higher concentrations of strontium as well. And so aragonite is isotopically depleted relative to, for example, high magnesium calcite or normal calcite or even dolomite. So some studies suggest that this offset between different minerals can be linked to the calcium coordination number in the calcium carbonate mineral lattice. On average, it seems that calcite is fractionated around -1.1 per mil relative to the fluid where it forms, and aragonite is more depleted, maybe around -1.5 per mil. So the third factor we need to think about is precipitation rates. And so I'm here highlighting 2 different studies. This is calcium carbonate precipitation studies in the lab. And what you see here is there's a really large range of delta 44 values. And that's because each of these studies were looking at the effect of the precipitation rate. So there is a huge dependence on precipitation rate. This study here, I'm showing you a figure where on the x-axis we have the growth rate of carbonate minerals, and then on the y-axis you have the fractionation factor. And so you see this pretty clear trend as we go towards higher rates of carbonate formation, we have more fractionation. If we want to extrapolate and extend this back to what would be the equilibrium fractionation, it has been inferred that this would probably be very close to 0 per mil. So if we have very, very slow carbonate growth rates, we would have almost no fractionation. A similar kind of relationship is observed if you look at strontium concentrations. So this is now another figure from a study by Tang from 2008, showing the effect of precipitation rates on both the fractionation factor of calcium and on the concentration of strontium in carbonate minerals. So higher fractionation higher precipitation rates leads to higher fractionation and more strontium, and vice versa. Finally, we also need to think about carbonate diagenesis. And so all the processes we've been talking about so far, they are all combined when we have to think about diagenesis. And so here I'm just highlighting some of the different archives that we have from recent carbonates that show this effect from diagenesis, where we have primary aragonite in the Bahamas, but we also have dolomite and hard ground cements that are isotopically enriched relative to the aragonite and high magnesium calcite. So what is happening during diagenesis? So with this figure, I'm trying to kind of simplify some of the different things that are going on. So first of all, if we imagine that we have some primary carbonate that forms in the surface ocean, this happens relatively fast. So when we're thinking about precipitation rates, this could happen over a diurnal cycle, over hours or a day. Aragonite would be more fractionated than primary calcite. And so when these primary minerals precipitate and they settle on the ocean seafloor, and we go into the pore space, we start to have early marine diagenesis. So this process is relatively slow compared to sort of what is happening in the water column. And so we can have the formation of cements or the recrystallization of primary minerals happening over timescales of thousands to millions of years. So what that means is because we have this very drastic difference in precipitation rates, is that our slow-forming diagenetic minerals will have a very low fractionation factor, close to 0 per mil. So these minerals would essentially adopt the isotope value of the pore fluid they're forming in. And so this would be a very different isotope signature to the carbonate minerals that are forming in the surface ocean, where we would have, in general, low calcium isotope values and probably quite a large range depending on the types of mineral we're forming. So we can also look at this process of carbonate diagenesis if we look at a cross plot of here strontium to calcium ratios on the y-axis and calcium isotope values on the x-axis. So here we see these are modern sediments from the Great Bahama Bank, and we have primary aragonite that's forming with low calcium isotope values and high concentration of strontium. And over time, this aragonite is recrystallizing and it's turning into either low magnesium calcite or dolomite. It's being dolomitized in some of these samples. So this process pulls calcium isotope values towards the value of seawater. And so this is happening during early marine diagenesis. The pore space is buffered by modern seawater, essentially. So that means that the carbonate minerals that are forming in these pore waters are essentially adopting a value that's very close to modern seawater, so close to 0 per mil. And we also see that we tend to lose our strontium through this process of diagenesis. So this is essentially our diagenetic fingerprint. And I'm going to come back to this in a little bit when we go and look at some Mesoarchean carbonates. So I think we have some idea of what is causing all this scatter in the modern. And it's not easy to pick apart these 4 different processes. So when we go back and look at the long-term record again and have to try and make sense of this scatter, we have to try and think about these different processes. And so to do that, I'm going to zoom in on the oldest record we have. So this is 2.8 billion year carbonates from the Mosher Formation. So these are carbonates I've been looking at for the last couple of years, and they are from the area around the Steep Rock Lakes in Ontario, near the town of Atikokan. And so this is essentially an old iron ore mine. They were mining banded iron formation back in the 1940s and going up to the 80s. In the middle here, you see an old photo of what these mining pigs looked like back in the days. So this is banded iron formation that's being mined. Today, these lakes are slowly filling up with water. So that this is a picture from today here on the right. This is a map of the area. So we have the 3 steep rock lakes. And the main mining operation took place here in the middle lake and the east arm lake. And in maroon here we have the banded iron formation that was being mined back in the days. And then underlying this banded iron formation, we have the Mosher carbonate formation. So this is a simplified strat column here to the right, where you see we have our iron ore and we have this underlying carbonate. And so the time constraints here come from the basement that is dated to around 3 billion years, and then an overlying ash from the formation a few hundred meters above the carbonate, which is dated to 2.780. So we went there, I think it was in 2019, and collected a bunch of samples. This was my first venture into Archean carbonates, and I must admit I was a little shocked about how ugly some of these rocks were. And here I'm showing you some of the examples of the really ugly rocks. So these have been extensively recrystallized. There was literally crystals growing out of the rock face in some of these scenarios. Also doing fieldwork in Ontario means a lot of bushwhacking. Most of these outcrops were covered in forest and moss and overgrowth. And it was actually hard to even see that this is a carbonate, to be honest. This is an example of some of the nicer looking samples in the field. So we could start to pick apart different primary features when we really got our eyes into the rock. So what you see here is there starts to be these striping looking features, which we think are actually crystal fans. And then there's this more sort of clothed feature below, which we think was actually some microbial framework, and the white calcite is filling up the pore space within this framework as early cements. Once we take these samples back and cut them open, polish them, get rid of all the weathering, we can start to see more things, and it's not as bad as it might have looked at first glance. So actually, when we cut these samples open, we can see these crystal fans much nicer. There were also some stromatolites. So this is an example of some of the columnar stromatolites that we saw there. And again, once you go back to the lab and cut it open, it's easier to actually see some of these features. So to understand the geochemistry of these rocks, we have to pick apart all these different alteration features. I hope I've convinced you by showing these photos that this isn't just a simple example of going out and finding the best preserved rock and then we can just ignore alteration, because these have all been extensively altered. The first thing we can see is just simply there are cross-cutting veins everywhere. So we have some kind of late stage alteration. We actually had some samples that were dolomitized and they had this zebra dolomite texture. So these black and white stripes, and in thin section we would see these saddle dolomite crystals. And so this indicates that we have late stage alteration. There's also a lot of silicification. So we had sort of chert nodules, which you can see here in black in some of these samples. But there was also just silicification sort of interspersed throughout the carbonate matrix, which you can see here in the thin section. We also had some features that we thought could maybe be primary. So we have these microbial early diagenetic pore-filling cements, which we call microbial fenestra. So the idea here is that this is some kind of microbial framework, and cements filled out the pore space in this framework relatively early, prior to compaction. And then that's why we have preserved this texture that we can observe. In some cases, this was not preserved. So we have, for example, in this photo here, it seems to be that the framework has collapsed. So the idea here could be that maybe in this case, early cements did not fill out the pore space prior to burial. And then we have some of these C4 crystal fans. And I'm showing you here sort of a close-up of some of these fans where we have these white stripes, in lack of a better word, which is essentially blocky cements that are filling up the space between the darker crystal fans. And in thin sections, these are large, blocky calcite crystals, we see a lot of twinning, which is indicating that these have also seen burial and higher pressure. So there's a lot of different things going on. Um, if I had to try and interpret what did the paleo environment look like for some of these samples, I'm imagining we have sort of these microbial maps with this net-like framework where we could fill out some um, calcite cements early on during early diagenesis. And then sort of out of these mats, we have these crystal fans that are growing on the seafloor. One thing that's really cool in the field, and these are not my photos, this is photos from Phil Frolick from 2015, is that we actually observe these large domal features. So this is a hat here for scale, and all the layers here are sort of vertical. And so we have these meter scale domal features that are made up of these alternating layers of microbial mats and crystal fans sort of growing on top of each other. So to look at the calcium isotope values of these samples, we went in and essentially micro drilled out a bunch of these different textures and a bunch of different hand samples across the steep rock lake area. And we specifically targeted all the different stages of diagenesis. So not just the nice looking features, but also the stuff that looked really altered. So I'm going to show you sort of a summary figure of what we found. So we have the range of calcium isotope values here on the x-axis, and these are now colored by their manganese to calcium plus magnesium ratio. First, we looked at some of these fans, the infill between the fans and the fans themselves. And in general, they were isotopically depleted. So they had low calcium isotope values, as low as -2 per mil in some samples. Um, on average, maybe around -1.6 per mil. A very few subset of these samples were dolomite, but most of these samples were calcite. Then we also went in and drilled out some of these different microbial fenestra samples and the sort of the micrite around this fenestra. And in general, these samples were isotopically enriched relative to the fans. We had values as heavy as maybe -0.5 per mil. And we also drilled out a bunch of the late stage features, so the veins and the supradolomites, etc. In general, for the later stage features, the calcium isotope values clustered pretty close to -1 per mil. So that would be the value of bulk silicate earth for reference. So I'm going to group these samples into three different categories. We have our late stage samples in the bottom, our fluid buffered samples that are isotopically enriched, and our rock buffered samples that are isotopically depleted in calcium isotopes. So let's think about interpreting this range that we observe. So to do that, I'm going to show you this cross plot of strontium to calcium plus magnesium ratios, so strontium concentrations on the y-axis, and this is a log scale, and then calcium isotopes on the x-axis. All the different colors here are some of these different textures that we microdrilled. The diamonds are the more well-preserved rock buffered samples, and the circles are our fluid buffered samples, for example, our microbial fenestra. And then in squares, we have our late stage samples. And then for comparison here in gray in the background, I'm showing you the modern Bahama data set that I showed you earlier. So this is our diagenetic fingerprint that I showed you before. So we have our fluid buffered samples that are have heavy calcium isotope values and low concentrations of strontium. So I think these are samples that formed during early marine diagenesis. They were essentially buffered by the influx of seawater through the sediment, through this microbial pore space. And they were adopting the calcium isotope values of that fluid, or at least very close to what that fluid had. Then we have our rock buffered end member. So these are samples that have low calcium isotope values. I think these recrystallized during burial in a closed system. So what that means is that although they have recrystallized, they're no longer primary aragonite, for example, they have preserved their primary isotopic values because they formed in a closed system. So we think that these seafloor seafloor fans likely were aragonite because they have this very low calcium isotope value and higher concentrations of strontium, which is characteristic for aragonite minerals. And then we also have a late stage end member that clusters here around -1, so the value of bulk silicate earth. So we think this is happening later on. These are our cross-cutting veins, for example. We can also look at a similar cross plot, still with calcium isotopes on the x-axis, but now manganese on the y-axis. And now you can really see these three different end members are standing out. So we have our rock buffered end member having the lowest concentration of manganese. Our fluid buffered end member has slightly higher concentrations, and our late stage end member has really high concentrations. So in general, we think manganese is enriched through the process of diagenesis. So that would explain maybe why some of these diagenetic end members have more manganese. But if you look at the gray samples here, so this is our modern samples from the Bahama Bank, these are actually orders of magnitudes lower concentrations of manganese compared to the Archean data set. So even our best preserved Archean samples have a lot more manganese than modern carbonates. The final cross plot I want to show you is looking at the correlation between calcium isotopes on the x-axis and carbon isotopes on the y-axis. And here we can again see these three end members. We have our rock buffered samples. These are our seafloor fans. And the carbon isotope value here is around 2.5 per mil. So pretty similar to modern aragonite from the Bahamas, for example. We also have a fluid buffered end member, which is around 1 per mil lower than our rock buffered end member. This is interesting because this is consistent with sort of the difference in the fractionation factor between aragonite and calcite for delta 13C. And then we have a late stage end member, which has both samples that are isotopically depleted and enriched compared to our other end members. So what I think we have here from looking at all these samples is essentially a preserved pore fluid profile through an ancient microbialite. Okay, so I'm going to try and step through this and put it together. So this is my interpretation of what this looked like. We have our microbial mat with this net-like framework that is infilled by early cements. We have our crystal fans, likely aragonite, growing out of this microbial mat. If we look at our calcium isotopes, this would be my reconstructed pore fluid profile through this map. So we have some calcium isotope value of seawater, here set to -0.5 per mil. As we go into this mat, we have our early cements that are forming in the pore space, and they are adopting the calcium isotope value of the fluid in that pore space because we have very little fractionation and this slowly precipitating environment. As we go deeper into the mat, our calcium isotope values will go lower in the fluid through this continuous dissolution of primary carbonate minerals. So that means when we get to our sediment buffered environment, the pore fluid is essentially fully buffered by the dissolving carbonate sediments. So any sediments that form here or any carbonates that form here will basically just adopt the calcium isotope value of that primary carbonate. We could do the same with manganese. So we have a pore fluid profile here of manganese. Our early diagenetic cements have slightly enriched manganese concentrations relative to our sediment buffered end member, which would be forming lower down here. This could be due to reductive dissolution of manganese oxides in the pore space during early diagenesis. And we have our carbon isotope profile, carbon isotope values of 0 per mil, looking pretty close to the modern. If we have any sort of remineralization of organic matter during early diagenesis, we could imagine that maybe our carbon isotope values would be slightly depleted in our fenestral cements. But once we go into our sediment buffered environment, we are just buffered by the composition of the dissolving primary minerals. So we preserve here our isotope signatures of carbon. So now looking at all these detail, I want to go back to this long-term record and see, can we pull out what is the seawater value of these Mesoarchean carbonates? And what does that mean for sort of our global calcium mass balance equation? So I think we can pull out the value of seawater. So this is my cross plot again, my diagenetic fingerprint with calcium on the x-axis, strontium ratios on the y-axis. And if you look at just the gray samples here, these are our Bohemian carbonates. We know that modern seawater is 0 per mil, and modern aragonite seems to be on average fractionated, maybe minus 1.4, minus 1.5 per mil relative to seawater. And then if you look at our Mesoarchean sample set, you can see that it's just consistently shifted to the left. And it's shifted to the left about half a per mil. So by identifying the fluid and sediment buffered end member in the Archean samples, we can reconstruct the seawater value of the Mesoarchean. So the difference between these two end members should be similar to the difference in the primary aragonite fractionation factor for us to feel confident that we are actually reconstructing seawater. And so you see we can essentially shift everything to the left, which would mean that Mesoarchean seawater would have a value close to minus 0.5. And that also fits with Mesoarchean aragonite having a value down to minus 2. And so our samples span this full diagenetic phase space of being fully rock buffered to fully fluid buffered. So I hope this is convincing and showing you that I think Mesoarchean seawater was half a per mil lower than the modern. And going back to our mass balance equation, this would imply that the bulk carbonate sink must have been about half a per mil heavier in comparison to today. Okay, so back to our model figure here with calcium isotope values of seawater on the y-axis, the fractionation factor on the x-axis. Today, calcium isotopes have a value of 0 per mil. So if we look at the equation, if our input value is bulk silicate earth, that means that our bulk carbonate sink must have a value that matches bulk silicate earth, so around minus 1 per mil. In the Mesoarchean, that means that our bulk carbonate fractionation factor must be around 0.5 per mil. Okay, so heavier than it is today. So what are some of the possible Mesoarchean bulk carbonate sinks that could have this net fractionation of half a per mil? So here I'm just listing 3 different hypotheses for what these could be. Maybe this could be veins in ocean crust, so carbonate veins in basaltic ocean crust. Maybe these are some kind of orthogenic carbonates. Maybe these are microbial mediated. And these could be forming in the pelagic realm, or maybe these are platform dolomites or fluid buffered carbonates. So I'm going to step through each of these scenarios and kind of discuss whether these fit with the observations. So on the right here, I'm now showing you a compilation of different modern samples that represent some of these different sinks. Now, of course, we don't have samples of ocean crust veins from the Archean, so this is not a perfect analogy. But at least if we look here at the spread of values of more recent ocean crust veins, you see that we have a pretty large range in the calcium isotope value, maybe going as low as minus 1.8 and all the way up to as close as modern seawater. The other thing I'm showing you here is that these are our Mesoarchean carbonates, so what I showed you before. So this is our rock buffered end member, our fluid buffered end member, and our late stage end member. One thing that's interesting, if you take the average of all these different samples that we measured in the Mosher carbonate, it is minus 1.1, which within measurement uncertainty is essentially bulk silicate earth. So let's say that ocean crust veins, although we don't actually really know what the fractionation factor would be, we look at the modern data. Let's assume that it is heavy, and this could be, for example, our heavy carbonate sink in the Mesoarchean. So if we go back and look at our mass balance equation, that must mean that we have sort of two different carbonate sinks. We have our veins, and then we also have our shallow carbonates because those are the ones I sampled. So we know they must also be there. And if the veins are the main um, carbonate sink, then to balance this budget, and we would have our shallow carbonates having to be isotopically depleted relative to the veins that would be uh, heavier because what goes in must come out. So the weighted average of these two sinks must have to equal what's coming in. And when we go and we look at the long-term record, or just if we look at the data from the Mesoarchean, we don't see a shift in our shallow end member to away from bulk silicate earth. We don't see this being significantly lighter. Actually, the average is pretty close to bulk silicate earth. So that suggests that veins uh, could not have been a large sink um, for calcium. We can kind of do the same exercise looking at orthogenic carbonates. And again, we don't have a perfect analogy to go look at in the modern. I think the best I could find here was sort of different methane seep nodules. There's a pretty large range. If we look at more recent samples, on average, maybe around minus 0.7 per mil. Um, some are heavier, some are lighter. Just reminding you that we're looking for a sink that has an average value around minus 0.5. We can do the same exercise with the veins. If the veins are a significant heavy sink, then we should also expect a shift in our shallow marine archive, which we don't see. Um, so if orthogenic carbonates, pelagic, microbial mediated, abiotic carbonates, whatever we imagine this sink to be, if that was important in the Archean, for the mass balance to add up, it must either have been small or insignificant, or it must have been isotopically similar to our shallow carbonate sink. And that's really the only way we can get the mass balance to work. So the third option, and I think my favorite option here is because it's just the simplest option, is that maybe the bulk carbonate sink was just platform carbonates. And these would be fluid buffered platform carbonates, so isotopically enriched. Um, and so this could be the dolomite or fluid buffered calcite. And so this hypothesis would be consistent with the data. If we look at modern platform dolomites, their average value is very close to half a per mil, and generally they're heavy. Um, so that fits the mass balance. And so none of this is to say that a pelagic or a deep water carbonate sink cannot exist, but the data does not require that. The data is perfectly happy to be explained just by having platform carbonates being the main sink. So if we go back and look at this long-term record again, I think there's a lot to learn from this record. And actually, if we go in and we look at the scatter, we can learn a lot about both the calcium isotope value of seawater and also the different processes that were operating at that time. So I think calcium isotopes is a tool for investigating the carbonate factory through time. And if we can go in and reconstruct the full spectrum of fluid to sediment buffered diagenesis, we can actually pick out what is the calcium isotope value of seawater at a given point in time. Um, one really interesting uh, conclusion here is that the calcium isotope value of the bulk sink in the Mesoarchean is very similar to essentially the pre-Mesozoic record, right? So there's not a huge difference here in our calcium isotope values that indicate that there should have been a shift in our bulk carbonate sink. And calcium isotopes, is a major element in calcium carbonate, and so you would expect calcium isotopes to reflect any changes in the bulk carbonate sink. So that brings me to my last slide, and thank you for attention. Also, thank you to my collaborators here, Phil Frolick and John Higgins, and different funding agencies that have supported this study.
All right. Thank you so much, Dr. Ahm, for a fantastic talk. We really appreciate you joining us today and sharing your work with the community. I'd like to open the floor up to any questions. So let's take a few seconds for everyone to gather their thoughts and questions. When you're ready, please raise your hand feature so we can call on you in order, or you can type your question into the chat. And Dr. Aim, if you need to head out at any point, just let us know so we can be respectful of your time. But we'll keep the discussion open until we run out of questions or you need to go. So thank you very much. Let's see, we have Francis with his hand up.
Hey, great talk on Sophie. I really liked how you were able to split apart all the different compositions with the textures. That was awesome. My main question, like your conclusions in terms of the carbonate sink seem to hinge on the values that you choose for the carbonization sink, the veins that you call them. And I was wondering, there was a huge spread you showed in the existing data. And what do you think the promise or direction could be to improve that value? And so I'm just looking at that carbon ocean ve crust veins. It seems like we really need to improve that value, perhaps.
Yeah, I think we do. I think in general we're just missing information here to really get at what this sink is. Um, There is, so Sasha Tershin has a bunch of ocean crust veins that are unpublished, and I've heard that they are in general heavy, but I have not seen the data set. I've only really seen these two data points here from an old study that suggests that these veins could be heavy. I think the veins, similar to our platform carbonates, we should probably expect a range depending on how much fluid is flushing through these veins. So we might have some that are fully fluid buffered towards seawater and some that are more sediment buffered. And we also seem to have a difference here in the mineralogy. So some of these are actually aragonitic and some of these are calcite. So that's also why we see sort of a spread in these values. But
And
yeah,
maybe when and where those are formed in the ocean crust as well. So it just kind of
yeah.
seems to me as a call to arms to get more data for ocean crust carbonates.
Oh yeah, for sure. I agree.
Yeah. All right, thank you.
Greg, you're next.
Yeah, that was great. Thanks. Very interesting. I was wondering, I don't know if you're aware of Tom Algio has a whole bunch of paleosalinity indicators that he uses. For example, boron to gallium and other ratios. I was wondering, do you actually have any evidence like that, that these are actually marine and not non-marine? And I ask because many banded iron formations in the Archean particularly are turning out to be lacustrine. Your textures don't look like typical stromatolitic microbial. They're kind of thrombolytic and kind of weird looking. Um, could they be non-marine, you think?
Who knows? I definitely don't have any proxies that would say like, this is definitely marine. I think one indicator that makes me lean towards them being marine, and I didn't talk about this at all in the talk,
Mhm.
but there's been a lot of studies looking at the cerium anomaly in these carbonates.
Oh,
Um, and actually, I'll show you here a summary slide, so a little teaser. Our sediment buffered, best preserved end members have a really clear negative serum anomaly. So these different colored lines here are our different textures. And then actually I'm comparing this here to modern carbonates in black. And so strikingly close to what it looks like in the modern.
and
And
that means reducing, right? Very reducing.
no, this actually would indicate, if we interpret it like we do today, that oxygen, essentially. Or in other words, we're forming manganese oxides that are removing some cerium from the water column.
Uh-huh, uh-huh.
Um, and so I don't think you expect to see that in a lacustrine environment where these serum anomalies often are not developed because it just kind of looks like the input, what's coming in to a lake, which would be closer to sort of bulk silicate earth.
Oh, fascinating. Thank you.
Yeah, thanks.
Thank you. Does anybody else have any questions? You've convinced everyone. Alex, you can go.
Thanks, John. You mentioned something about early on. Thanks for a really cool talk. You mentioned early on about precipitation rate having an influence, and I had to walk away at some point for a minute or two. So sorry if I missed this. But do you think precipitation rate changing or being different in the past, like on average, could have an influence?
Yeah, I think um, it's a really good question. And I'm hoping that actually, if we look at this record again, that there is something about precipitation rate to maybe pull out of this record. The first thing we have to do is kind of reconstruct the different diagenetic end members because when we think about rate, the biggest differences in rates are really what's happening in the surface versus what's happening during diagenesis. Um, but I'm curious if sort of the spread of data we see within a single time bin could could tell us something about this difference between the primary environment and the water column and what's happening in the pore space. Um, it's not something that's been done or something that I've tried to do, but I think if we really dig into this record, there might be something there to pull out.
Cool. Thanks a bunch for a great talk.
Yeah, thank you.
Paul?
Yeah, excellent talk. My question is, how large is the temperature dependence of the fractionation factor? And does that play any role in the Cenozoic change?
Yeah, I actually put in a slide here. So, does temperature affect calcium isotope values? So early on, when the proxy was sort of first proposed, the idea was that maybe this is a temperature proxy. But there's been a lot of studies later on that shows that it's really not, it's re very weakly depending on temperature. So we are talking sort of like uh, less than 0.01 per mil per degree. So it's not something that we would expect to really influence the record.
All right, awesome. Anybody else?
Hi.
Oh, too high.
Hey, sorry.
Too high.
Yeah, great talk. Maybe I missed this. I wonder whether you talked about uh, the proportion of aragonite versus calcite precipitation might have an impact on the observed low calcium isotope value in Archaea, or maybe that's part of your sediment buffer diagenesis.
So you're thinking the proportion of aragonite versus calcite influence the seawater value?
Yeah.
Yeah. I mean, it should, because aragonite versus calcite would have a different fractionation. So if you are in a, sort of an aragonite sea versus a calcite sea, we would expect that to be evident in the long-term record, right? Because we would expect for an aragonite sea, we would be removing more isotopically depleted calcium, which would dry seawater heavy. Now, this is not clear from the record, which I think is interesting. And maybe one of the things that kind of complicates this is that whether it's aragonite or calcite that are deposited in these platforms, they're all being diagenetically altered before they're, buried. And so maybe the main burial sink is simply our fluid buffered platforms, so that we don't actually see this difference between our aragonite and calcite seeds, which you would expect to see if they were sort of buried in their relative
Or the
ratios.
dolomite. The dolomite, there's obviously more dolomite in Precambrian.
Yeah, there is. So we would
Ultimately
expect that to be heavier. Yeah, I think those are good questions, and I think it's really interesting that we don't really see it in the record as sort of standing out. Um,
Okay. All right. Great talk. Thank you very much.
yeah, thank you.
Thanks.
All right, the next hand up is Robin.
Hi. Yeah. Thank you very much for your talk. Early on in the talk, you discarded the biomineralization effects because in the Archean, there are no skeletal carbonates precipitated. I was wondering if you knew about microbialite carbonate, or well, biomineralization effects for microbialites, because with EPS, the organic molecules that can absorb and trap calcium and all those kind of things that could fractionate calcium isotopes. And in the review of the different carbonate types, I don't think I saw microbialite calcium isotope uh, composition. So do they exist except from what you showed from your study? And do some like maybe laboratory or I don't know experimental work exists to constrain how biomineralization could affect calcium isotopes in microbial carbonates?
Yeah, great question. You're totally right. I unpurposely just ignored that part. Um, there are a few studies that have looked at this, and mostly these were studies that sort of combined looking at the microbial fractionation and then also looking at sort of proto-dolomite and the fractionation of that. And it seems like there is maybe a small fractionation, but it is small relative to sort of aragonite and calcite, maybe on the order of half a promille. And then on top of that, if we then also have dolomite forming, it seems to be an additional half a promille. There's not a lot of studies, though, looking at this, so I think there's definitely more work to be done. But it is possible that there is a small fractionation happening here as well. Um, but again, this would then go through this sort of diagenetic window where it could also be uh, pulled heavier again as we go into the deep record.
Okay, thank you.
Yeah, thanks.
Thank you. And any last questions, or we say thank you and I'll go on our way? Uh, Thank you for joining us today. It was a wonderful talk and a wonderful discussion. So thank you and have a wonderful day, everybody.
Thanks.